I've grouped this next lot of functions according to powers of x. And while I've said here that we're going to look at sketching functions with higher powers of x, I've included some where obviously now we've got x to the power 3, and then we're going to do x to the power 4 and make some conclusions about other higher powers. But also what I've included in this little section is x to a fraction, so a power of a fraction, so x to the half. So I don't think it's a higher power than what we've had. It's a fractional power. And we're also going to look at when the power is a negative. So fraction and negative powers as well as some higher powers. So you saw that linear is x to the power 1, quadratic is x to the power 2, cubic x to the power 3. Now, the basic cubic graph was introduced in stage 5 and it looks like this. You'll see that we're going to develop that from just y equals x cubed into something much more complicated. For example, we might have y is equal to x plus 2x minus 1 and x plus 3, or x minus 3, I'll change that. Now we can see that would also be a cubic, because x times x times x would give x cubed. There would also be some x squared terms, there would be some x terms, and there is a constant. So we would end up with, in general form, ax cubed, we'd have some number of x squareds, we'd have some number of just x terms, and we would have a constant. And you can probably see the constant is 2 times minus 1 is minus 2, minus 3 is plus 6. D would actually be equal to 6, just as a point of interest. When we get onto those, you can see that that cubic is going to cut the x-axis, which means y will be naught. So the solution to y being naught, there are 3 solutions. If x was equal to negative 2, y could be naught. That's where on the x-axis. X could be 1 and x could be 3. Now, that means the graph is going to cut at 3 places, and we get something like this happening. And you will get to learn that this is a very common cubic, and this is the other cubic shape. So we've really got 3. We've got the basic cubic that looks like that when it's passing through the origin and it doesn't have all these other turns. Or we've got a positive cubic that will have 2 turns, or a negative cubic which also has 2 turns, 1 turn, 2 turns, and it will graph to look like that. The 4th power of x is interesting also. If you've simply got the 4th power of x and little else going on, so for example, straight out y is equal to x to the 4th and no other terms, it's I guess the general form would be y is ax to the 4th plus bx cubed plus cx squared plus dx plus then a constant. Now this is much more complicated, much more complicated, more difficult to sketch. The very basic y equals x to the fourth power, where these are all 0, b is 0, c is 0, d is 0, e is 0, it graphs to a very flat bottomed parabola. So then what we actually find is then every even powered x function with no complication to it, no x to the fifth term, fourth term, third term, none of that, will also graph to be a parabola. And its bottom is even flatter again. So just an interesting fact that x squared, x to the fourth, x to the sixth, x to the eighth, solely by themselves graph to give an increasingly flattened bottom U shape. Also in this little grouping that I've created and some questions to go along with it is when x has a fractional index. Now, hopefully you know that y equals the square root of x is exactly the same as y is equal to x to the half. Square root is the indice a half. So looking at it in either of those formats, remember when we take and it's given as the square root, it's understood to be positive. Some students recognize this as the positive half of y squared equals x. If I was to square both sides, I would get y squared equals x. Now, we haven't done, some of you may have touched on this, and it's great if you have, but if some of you haven't looked at this equation, you probably won't know that it is a parabola on its side like this. We know that y equals x squared is a parabola like this. Then when you swap the x and the y to be x is y squared, the parabola goes to its side, and if you then take the square root of both of those, so it goes back to y to square root, then it is just, as you can see here in the graph, the positive side of the parabola. The other graph that I've also grouped into here is a circle, because we've got powers of x, we've got both x and y are both squared, giving the radius squared. Hopefully you've seen that equation before. What we know is that this is not a function because it doesn't pass the vertical line test, but just familiarise yourself at the moment for now with something in this format, and to become more familiar, then you need to note the details. We have had x squared before, but we certainly haven't had both x squared and y squared in the same equation equaling, for example, 9, a number squared there. When you have both x squared and y squared, you know it's going to graph to give you a circle. And again, we'll do a lot more on that relation, really. It's not a function, on that relation. And leading on from that, the semicircle then becomes, if I was to make y the subject of this, so I've got y squared would be 9 minus x squared, and then take the square root of both sides. Then we've got the positive square part of the circle, which is a semicircle. So we could have y is the square root of a, just being some constant, minus x squared. So an example is if a is equal to 3, if a is equal to 3, then we've got that. And so you would have the top half of the circle radius 3, not 9, radius 3. If a was equal to 3 again, with the minus at the front of the square root, then we have the bottom half of the circle from minus 3 to 3. That is if a is 3 and a squared is 9. I think there's one more in this group, and that is the hyperbola. Now, hyperbolas are usually written in the form y equals 1 on x. Well, that's the very most basic. And remember, that is x to the minus 1. So looking at a power of x as a negative number, and in that case, the graph will fall into the family called hyperbolas. We have asymptotes. Both the axes of symmetry are asymptotes. That means the graph gets closer and closer, but it doesn't actually ever cut it or meet it. As x goes to infinity, now this is a good practice at understanding notation. X at forward arrow infinity. That means we're heading off in this direction here. And this says, as x heads to plus infinity, y is heading to naught. Yes, it's trying to get to the x-axis. Remember, the x-axis is y is equal to naught. That makes the positive x-axis an asymptote. As x tends to naught from the positive side, so we're coming here. So x is trying to get back to naught from the positive side. Where is y going? Y is going up here. As you can see, y is going up to infinity, and that's what it's indicated here. Y is heading to plus infinity. So it actually makes the positive y-axis is also an asymptote. As x heads to negative infinity, so x is going down here to negative infinity, where is the graph trying to get to? The graph is trying to get to y is 0, so it makes the negative x-axis an asymptote. And as x now heads back to 0 from the negative side, so x is coming here, what is the y value doing? The y value is going down here, and we would say that is negative infinity. And so that makes this negative sorry, that should have been a negative there, isn't it? The negative y-axis is also an asymptote. Now, hopefully you'll just pause this video, rewind this video, listen to this several times until you've got all of that sorted.